Let G be a graph with a Hamiltonian path. If k vertices are deleted from G, then the resulting graph has at most k plus 1 components. Remember that a Hamiltonian path is a path containing all vertices of the graph. So we'll be proving this result in today's Wrath of Math lesson. This is a viewer-requested video. You can see in the request on screen now that there were two questions. We're going to prove this one first because it's going to help us prove the other result, which we'll probably prove in the very next lesson. This is a fairly straightforward induction proof. We're going to use induction on the number of vertices in the graph, so I definitely recommend giving it a try yourself before watching the rest of the lesson. Just before we get into the proof, let's quickly see a little example of this result in action. Here is a graph with a Hamiltonian path. Just to make it a little more interesting, let's add one more edge. Clearly, there is a Hamiltonian path in this graph, a path containing all of the vertices. If this result is true, which of course we will prove that it is, then removing any k vertices from this graph should leave us with, at most, k plus 1 components. So if we delete 2 vertices, for example, then we should have at most 2 plus 1, or 3 components. Let's give it a try. Suppose we delete this vertex here, and of course its incident edges, and then this vertex right here. What are we left with? Well, we've got 1, 2, 3 components, and of course 3 is less than or equal to 3, so the result checks out. So hopefully that gives you a better feeling of what this result is stating if you weren't totally sure. With that said, let's actually prove it. We'll begin, of course, with the base case of the induction proof. We want to begin by considering all graphs of order n equal to 1 that have Hamiltonian paths. Of course, there's only one such graph, the graph with a single vertex. This graph, of course, has a sort of trivial Hamiltonian path of length 0. We want to show that deleting any k vertices from this graph leaves us with at most k plus 1 components. So in this case, k could be equal to 0, we could delete no vertices, or k could be equal to 1, we could delete one vertex. If we delete no vertices, then our result tells us that we should have at most 0 plus 1, or 1, components. And indeed, that's true. If we delete no vertices from this graph, we've got exactly 1 component, so that's true. If we delete one vertex from the graph, the result tells us that we should have at most 2 components. If we delete one vertex from this graph, we're looking at the null graph, the graph with no vertices or edges, which we will define to have 0 components, so of course this does fit the condition. 0 is less than or equal to 2, so looks good. And of course, some authors might not even define the null graph to be a graph, so this might not even be worth considering for some authors. And of course, by starting our base case with graphs of order 1, we're sort of ignoring the null graph to begin with. It's not very interesting. Now, of course, proving the result for our base case is enough to now move on to the induction step. But let's just quickly take a look at the next case where n is equal to 2. The only graph of order 2 that has a Hamiltonian path is this graph here. Let me also redraw our graph of order 1 above. So in this graph, k, the number of vertices we delete, could be equal to 0, 1, or 2 if we're considering the null graph. If we delete no vertices, then the resulting graph should have at most 0 plus 1, or 1 components. And of course that's true. Deleting no vertices leaves us with exactly 1 component. If we delete one vertex, then we should have at most 1 plus 1, or 2 components. And if we delete either one of these vertices, we have 1 component, and 1 is less than or equal to 2, so that checks out as well. If we delete 2 vertices, we should have at most 2 plus 1, or 3 components. Deleting 2 vertices from this graph once again leaves us with the null graph, which we're saying has 0 components. 0 is less than or equal to 3, we're good to go. Now, I would encourage you, before watching the rest of the lesson, to try looking at the case where n equals 3. This is where things get a little more interesting. There are 2 graphs of order 3 that have a Hamiltonian path. The path on 3 vertices, and the cycle on 3 vertices. Try showing that our result is true for these 2 graphs as well. For the purposes of this video, we're going to head on to the induction step now. So we'll just begin the induction step by saying assume the result is true for all graphs with Hamiltonian paths and fewer than n vertices, where we can say that n is greater than 2 because we already proved the result is true for all graphs with one vertex and two vertices that have Hamiltonian paths. And so, of course, if you prefer, instead of writing greater than 2, we could write greater than or equal to 3. Then, to complete the proof, all we have to do is show that for all graphs that have Hamiltonian paths and n vertices, deleting any k vertices from these graphs leaves us with at most k plus 1 components. So we'll start off by taking a graph of interest, as in let G be a graph of order n. And then also, of course, importantly, let G be a graph of order n with a Hamiltonian path, a path that contains all the vertices of G. And now let's go ahead and name that Hamiltonian path. We'll call it P, and let's name its vertices as well. Remember that these are all the n vertices of G. We'll call them V0, V1, V2, and so on, all the way up through the second to last vertex on the path, Vn-2, and then the last vertex on the path, Vn-1. Note that this is a total of n vertices. These are all n vertices of G, since P is a Hamiltonian path. We want to show that deleting any k of these vertices from the graph will leave us with at most k plus 1 components. So to start talking about deleting k vertices from the graph, let's let S be a subset of the vertex set of G, and we'll call the cardinality of S k. So S could contain any number of vertices that we could possibly delete from G, ranging, of course, all the way from 0 up to the maximum number of vertices we could delete being n, all the vertices. Then, of course, our goal becomes to show that the number of components in the graph G minus the set S of k vertices, the number of components in this graph, is less than or equal to k plus 1. And let me just point out the notation here, because I know it can look a little confusing in this problem. K is the number of vertices of S. It's the cardinality of S. But this notation, K of a graph, is common notation for the number of components in the graph. We won't have to use this notation a ton in this proof, so I think it'll be pretty easy to follow what it means when it does show up. So this is what we want to show. I'm going to go ahead and erase it, and we'll get on with the proof. So this is a proof with two pretty straightforward cases. Case 1 is where the second element of the Hamiltonian path, V1, is not an element of that set S that we're deleting from the graph. If this second vertex of the Hamiltonian path is not an element of the vertex set we're deleting from G, then it's pretty easy to prove our desired result. And here's how we do it. Consider our graph G, but without that first vertex of the path V0. And suppose we delete this vertex set S from this graph. So if we look at this graph, G minus the first vertex of the Hamiltonian path, V0, then subtract this vertex set S, how many components does this graph have? And instead of parentheses, let me actually use square brackets there. So how many components does this graph have? Well, we can use our induction hypothesis to answer that question. Because here are the two important things to notice. G minus V0 obviously has fewer vertices than G, because it's G without that one vertex, V0. Additionally, G minus V0 is a graph with a Hamiltonian path, because the part of our original Hamiltonian path P following V0 is a Hamiltonian path in G minus V0. So we can apply our induction hypothesis to this graph to say that if we delete k vertices from the graph, the number of components in the resulting graph has to be less than or equal to k plus 1. And in fact, it's possible that we're deleting fewer than k vertices from G minus V0 when we subtract S. Because S, remember, has k vertices, but if one of those k vertices is V0, then that's not being subtracted from G minus V0 because V0 already isn't in G minus V0. So it's possible that when we delete the vertex set S from G minus V0, we're actually only deleting K minus 1 vertices, in which case we could have an inequality of less than or equal to K minus 1 plus 1, or K. But we don't know if V0 is in fact an element of S or not. We know, of course, that V1 is not an element of S, but we don't know about V0. So we have to go for the upper bound that we know for sure will be true of K plus 1. And then it's very easy to finish this case of the proof. Since V1 is not an element of S, we know that V1 is a vertex of this graph that has at most K plus 1 components. So V1 is an element of the vertex set of G minus V0 minus S. So in other words, some component of G minus V0 minus S contains V1. Then we know for sure that the number of components in the original graph G minus S is also less than or equal to K plus 1. And we know that because if V0, the first vertex of our Hamiltonian path, is not an element of S, then it will be in G minus S, and of course it will belong to the same component as V1, because V0 is adjacent to V1. So going from G minus V0 minus S to G minus S will not increase the number of components, since again, some component of G minus V0 minus S contains V1, and V0 will just be in that component because it's adjacent to V1. On the other hand, if V0 is an element of S, then G minus S also must have the same number of components as G minus V0 minus S, because in that case they would be the same graphs. So again, the number of components in G minus S would be less than or equal to K plus 1. And notice that we basically just went over two subcases of this case. The first subcase is where V0 is not an element of S, in which case we know this inequality is true because V0 will be in the same component as V1. So this graph, G minus V0 minus S, had at most K plus 1 components, and once we add V0 back in, we won't change the number of components, so it's still less than or equal to K plus 1. And then if V0 is an element of S, then G minus V0 minus S and G minus S are the same graphs. And so of course this inequality holds. And remember that we got this very important inequality from our induction hypothesis. Alright, feel like I spent a little longer on that case than I wanted to, but let's move on to case 2 of the proof and then we can wrap it up. And before moving on to case 2, just for convenience, let's copy and paste our Hamiltonian path, just bring it down for reference purposes. So this is case 2. Remember that we want to show deleting the k vertices of S from G leaves us with at most k plus 1 components. The first case is when V1 is not an element of S. So now case 2 will be where V1 is an element of S. Remember in case 1, we applied our induction hypothesis to the graph G minus V0. For case 2, we're basically going to apply our induction hypothesis twice to two different graphs. The first graph is G minus V0 minus V1, so the graph G without the first two vertices of the Hamiltonian path P, and of course without their incident edges as well. So I'll drag that over to the right, and then the other graph we're going to apply our induction hypothesis to is G minus V2, V3, V4, and so on, which instead of writing its name like that, we could do quicker to just draw the graph. It's got the vertices V0 and V1, and they are joined by an edge, since they're adjacent in this path. And in fact, this graph is simple enough that we actually won't need to use our induction hypothesis on it. We'll just have to do a quick analysis of it. So basically, as a super quick explanation of what we're about to go over in detail, we're going to show that this part of the graph can have at most one component after we delete the vertices from S from the graph, and then this part of the graph can have at most k components once we delete the vertices of S from this graph. So then combine them together to form G minus S, and that could have at most k plus 1 components, but it might have fewer components, because in the original graph G minus S, there might be some edges joining these vertices to the vertices of this graph, which would reduce the number of components further. But certainly the number of components is at most k plus 1. So that's just a quick summation of what we're about to do. Now let's do it. We know, of course, just at a glance, looking at this graph here, that no matter what vertices we delete from it, it can have at most one component. If we delete no vertices, it's got one component. If we delete one vertex, it has one component. And if we delete two vertices, it's got no components. So this is kind of an abuse of notation here, but we're going to write it like this. The number of components in this graph minus the vertices of S is certainly less than or equal to 1. Whatever vertices of S are getting deleted from this graph, we're definitely going to have no more than one component. So we can set that to the side a little bit and now focus on this graph. And let me bring that a bit more to the center. For this graph, we of course want to know how many components this graph is going to have once we delete the vertices of S from it. So we want to know a bound for the number of components of G minus V0 minus V1 minus S. So we'll write that like that. There we are. That's the number of components in the graph G minus V0 minus V1 minus the vertices of S. So can we apply our induction hypothesis to this graph, G minus V0 minus V1? Indeed we can, because of course it's got fewer vertices than G does, since we've deleted two vertices from it. And G minus V0 minus V1 has a Hamiltonian path, because the part of our original path P from V2 to Vn minus 1 is a Hamiltonian path of G minus V0 minus V1. Because of course all of these vertices from V2 up to Vn minus 1 are the vertices of this graph. So we can apply our induction hypothesis. If we delete any k vertices from this graph, the resulting graph can have at most k plus 1 components. However, and this is the cool part, we know that we're not in fact deleting k vertices from this graph. We're only deleting k minus 1 vertices from this graph. That's because all the vertices of S are getting deleted from this graph. But one of the vertices of S is V1, which is already not in the graph. It's been removed already. So when we subtract S, we're not deleting the k vertices of S, because one of them has already been removed. Instead, we're deleting at most k minus 1 vertices. It's of course possible that V0 is also an element of S, in which case we're deleting even fewer vertices, since V0 has also already been removed, but we don't know that. We know that at most, from this graph, when we subtract S, we're deleting a maximum of k minus 1 vertices, which means when we apply our induction hypothesis, we can say that the number of components in this graph minus S is less than or equal to k minus 1 plus 1, or k. I think there's some potential for confusion here. You might think, well, wait a minute, aren't we really deleting k vertices since we're deleting V0 and V1 and all the vertices of S? We might even be deleting more than k vertices. But if you're having that confusion, remember that we're applying the induction hypothesis to the graph G minus V0 minus V1. So don't think of V0 and V1 as vertices that are being deleted. They're vertices that aren't in that graph. And so when we then delete all the vertices that are in S from this graph, we're only deleting at most k minus 1 vertices, since one of the vertices of S, V1, is not in this graph. So hopefully that helps clear it up. And then these two facts together mean, of course, that the number of components in the original graph G that we're actually interested in, minus that set S of k vertices, has to be less than or equal to k plus 1. Because at most, G minus S will have all 1 components of this graph and all k components of this graph. but it's possible that in G, where these two pieces of the graph are brought back together, that G minus S has fewer components, because V0 might be adjacent to some vertex in this graph. But even if it isn't, that only gives us one more component to a graph that had k components, so we bring these pieces back together to the original graph G, subtract S, and we're going to have a maximum of k plus 1 components. There are more elegant proofs of this result, but there are a number of things I like about this one, and that is the end of the proof. We've just proven that for a graph of order n, that has a Hamiltonian path, deleting any k vertices from that graph results in a graph with at most k plus 1 components. And so by induction, we've proven our result. If G is a graph with a Hamiltonian path and k vertices are deleted from G, then the resulting graph has at most k plus 1 components. So I hope this video helped you understand how to prove this fun graph theory result. Let me know in the comments if you have any questions, need anything clarified, or have any other video requests. Thank you very much for watching, I'll see you next time, and be sure to subscribe for the swankiest math lessons on the internet.